Welcome, this is going to be our lecture video for January 5th. Let's go ahead and get started, get those notes out. Our goal for today is to be able to simplify single radical expressions. Why are we doing this? So we can apply the properties of square roots to make a term easier to compute. So a square root is just a type of radical. Radical can refer to roots of any index. So a square root would look like this, and we could say there's a little 2 out in front. It's asking what number when squared equals the part that's underneath. We're going to call that our radicand. But we can go higher. We can have a cubed root, we can have a fourth root, and so on. And our goal today is to simplify these. Now really what that means is make the part underneath as small as possible. And we do that to make them easier to compute. If you actually needed a decimal approximation of these radicals, the smaller the number underneath the radical, the easier it's going to be to actually get those decimals if you're doing it by hand. And then kind of the other reason we want to simplify radicals is because on the SAT and ACT, all of the answer choices are always going to be the simplified version of whatever you're computing. And if it includes a radical, it'll be simplified. So you need to be able to do that because you could do all the other steps right, but if you can't simplify it, you won't be able to pick the right answer. Anyway, go ahead and pause the video. Here I've got a table of our most common powers. So perfect squares, perfect cubes, perfect powers to the fourth and to the fifth. Having a table like this, someplace you can flip to, can really speed you up. Just these numbers here is enough to be able to shortcut most all simplification problems. All right, and the reason I'm having you copy this down is because when I want to find a cubed root, I need to first find any perfect cubes that go into the radicand. It's really helpful to have a list of some perfect cubes here so we can see if any of these divide in evenly. Okay. So I've been using these words index, radicand. I think now would be a good time to add those words into your notes. The index is the number out in front. If it's a square root, the index, if we don't see anything, it's said to be a 2. So if we don't see anything, the index is 2 because it's a square root. And go ahead if you need to pause and get the rest of these parts down so we can be using the right vocabulary. Just for fun, what is the cubed root of 27? Well, you could even go back to this table here. So 27 is 3 cubed, so the cubed root of 27 is 3. All right, so 2 more properties, 2 more things for you to copy down. A lot to copy down at the start of this unit, but then we'll be able to start doing practice problems with it. So let's just get this all copied down. One thing you need to know is the product property of radicals. Essentially, if 2 things are being multiplied underneath a radical symbol, you can distribute that radical symbol to both of the things. Here we've got a times b all underneath the square root, that it becomes the square root of a times the square root of b. So we can split apart radicals as long as it's only multiplication underneath. This does not work with addition or subtraction. All right, and then a property that doesn't have a name when you look it up, so I call it power negation. And that's the idea that a square root can cancel out a squared, just like this, or a cubed root can cancel out a cube, just like this. So the cubed root of x cubed is just x. The cubed root and the cube cancel out. Okay, so with these 2 properties, we're going to be able to simplify a bunch of different radicals. We'll start with this. I want to simplify the square root of 32v. Now you might look at this and say, well, that looks already pretty simplified. How can we go any further? Well, the thing is, we'll write this as our goal, is to get the smallest radicand possible. So if we can bring anything out from underneath the radical symbol and write it out in front, that counts as simplifying it, even though it might look a little bit more complicated. We don't really care if the overall expression looks more complicated, just the part underneath the radical symbol. Because this, if we were to actually compute this and we wanted a decimal value, this would be the really difficult part, is figuring out what number squared equals this quantity here. It's 32v. Okay, so this is a square root, it's a square root. The index is 2. That means we want to look at that table we just wrote. We want to look at the perfect squares. So let's write that here. We want to look in this column. All right, so your perfect squares, it starts with a 1, but taking out a 1 doesn't change anything. So we'll go 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. We've now exceeded 32, so we don't need to keep going. We want to look, are any of these, we want to actually look for the largest factor of 32, the numerical part of the radicand. So 4 fits into 32 evenly, but so does 16. So the largest factor of 32 is 16. Okay, so 16 is 4 squared. So if we can get the 4 squared by itself, the square root of 4 squared would be just a 4. We can cancel out that squared, and we can cancel out the square root. So here's what we're going to do next with our square root of 32v is we want to split up that 32v into a 16 times 2. And then got to keep the v. The v is just going to stay underneath the radical symbol. There's no way to get that out from underneath. But now that I've split up the 32 into a 16 times 2, I can use that product property to kind of, it's not really distribute, it's factor out the square root. No, it's distribute. We're distributing the square root to 16 in the 2v. All right, so we distribute the square root, and then with just this part here, square root of 16, we know that that is 4. So we write that as 4 root 2v. Now you might be saying, well, isn't the square root of 16 technically plus or minus 4? And yes, that is true, but we're going to kind of forget that rule for this unit and just deal with the principal square root, which is to just keep the positive. So yeah, we'll say only keep positive 4. And this is actually totally okay because this square root here, which would still be multiplied by, still denotes that this is positive or negative. So this part here will be positive or negative, making the overall expression positive or negative. So it's not really necessary to put that little plus or minus in front. Only keep positive 4 in the simplification. Okay, so this is fully simplified. I know it doesn't look all that much smaller, but it is considered to be more simplified because we've got a smaller radicand, which is all that really mattered. All right, let's keep practicing this. Square root of 64 times x squared. So 64 is a perfect square. 64 is 8 squared. So I'm going to distribute this square root to the 64 and to the x squared. All right, square root of 64 is an 8 because 64 could be expressed as an 8 squared, and then the square root and the squared you can cancel out. But over here, we can actually simplify this as well again. square root and a squared cancel out, so this just becomes an 8x. Now here, maybe you do want to include the plus or minus, because now there's no square roots left in the final answer. So that there's no square root left to encode the fact that this is a positive or negative. So I don't know. Most of the time you'll actually see this left off in simplifications, but if we want to be the most technically correct, we need this here, especially if there's no square roots left. So I'll just say keep a plus minus if no square root left. Okay. Hopefully that's clear. All right, let's do another one. Index is still a 2. We're still doing square roots, so we're looking for perfect powers of 2 that we can pull out from this. So let's say I didn't copy down that many perfect powers of 2. I just got 4, 9, and 16, and I don't have enough to go all the way up to 196. Well, it's okay if we take out a number that's not the largest perfect square factor of 196, as long as we check again to make sure that there aren't any more left. So I might have only copied these ones down here, but I do see that 4 fits into 196. Well, let's take out just the 4 and see then if there's anything left. So 196 divided by 4 is 49. So I can split this into a 4 and a 49. We'll keep this all still under the square root. Now what do we do with this r cubed? Well, a square root can only cancel out an r squared. It can't cancel out a cubed. But one thing I could do is I could rewrite that r cubed as an r squared times an r. Now there's still 3 r's here, so it's still equivalent. But the square root will be able to cancel out this squared. Unfortunately, this r will be left behind. Okay, now let's distribute our square root. So square root of 4 times the square root of 49 times the square root of r squared times the square root of r. Now, right here, we took out the 4 because we knew 4 was a perfect square, but it turned out when we took out the 4, what got left behind, 49, that's also a perfect square. That's 7 times 7. So square root of 4 is a 2, square root of 49 is a 7, square root of r squared is an r, and square root of r just gets left alone. This one we won't be able to remove from the radicand. There's still going to be a square root in our final answer. The 2 and the 7 can be put back together. That becomes a 14r root r. And when it's a square root, you can just say root, and it's implied that it's a square root. So 14r root r. And that is fully simplified. There's still that square root there, but it's the smallest radicand possible. Okay. Now another problem. This time we see we've got an index of 3. So with that index of 3, we want to be looking at perfect cubes to see if we can take any of these out. So 1 cubed is 1, but taking out a 1 doesn't change anything. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and that should be enough. I guess we could do 5 cubed, 125, but yeah, we're not going to find any more. I believe, let's see, does 64 fit in evenly? 192 divided by 64, it does. It fits in 3 times. 3 is not a perfect cube, so we know that that is the largest one. So I can split that 192 into a 64 times 3. 64 times 3 still equals 192, but 64 is a perfect cube. It is specifically 4 cubed. All right, and then with the n to the 8. Again, a cubed root can't cancel out a to the power of 8. It can only cancel out to the power of 3, but I can split apart that n to the 8 into an n to the third times n to the third times n squared. There's still 8 n's here. 3 plus 3 is 6 plus 2 is 8. But if I distribute the cubed root to these n cubes, I'll be able to do some power negation. So now I've got the cubed root of 64 times the cubed root of 3 times the cubed root of n cubed times the cubed root of n cubed times the cubed root of n squared. So you can distribute that. Cubed root of 64, well, 64 is the same as 4 cubed. So cubed and the cubed root cancel out, and this just becomes a 4. Cubed root of 3 has to say cubed root, but again, we can cancel here and here to get times n, and cubed root of n squared will have to remain as a cubed root. All right, now we're going to put this all back together. So we want that 4 out in front, kind of like a coefficient. N times n can be put back together into an n squared. And then we have to write everything that left behind underneath the cubed root. There's still 3 and an n squared underneath. So the fully simplified answer, and again, it doesn't look more simplified, but the radicand is smaller, is 4n squared cubed root 3n squared. All right. Now let's do a crazy one with an index of 7. So a 7th root can only cancel out a to the power of 7. So we need to see how many to the power of 7s we can write out of these 3 variables. Now we've got multiple variables too. Let's not let that throw us off. Okay, everything's being multiplied, so I will be able to distribute this 7th root. Here's how I want to do it. I want to split apart that x to the 23rd into as many x to the 7ths as I can. So x to the 7th times x to the 7th, I'm up to 14 x's, times x to the 7th, I'm up to 21 x's, so x squared, and now I still have 23 x's just split apart. Now, y to the 14th, same thing. I want to split that into as many y to the 7th as possible. I can get 2 of them. And then z to the 8th will become z to the 7th times z. All right. Now, this will become just an x times just an x times just an x times a y. This will become just a y, and this will become a z, but then this x squared and this z here are going to get left behind, and these here can be put back together into just a single variable with an exponent, and we'll write those out in front. We'll go in alphabetical order. So now we've got an x cubed from these ones here, y squared from these two, and a z. Those all jumped out of our 7th root. But left behind was an x squared and a z. These guys here got left behind inside the radical. They weren't able to jump out like these x's, y's, and z were able to. All right, box around that, and that is considered to be more simplified because it's got the smaller radicand, only an x squared z, even though it looks kind of longer. All that we cared about is getting that smaller radicand. All right, I'll embed a few more problems here. We'll call that good for this lecture video, and have a good rest of your day.